You'll notice that the very first video that I posted is labeled as optional and is a introductory video for these forces that we're going to be talking about from one of my summer courses, which was a 100 level course. I thought it did a pretty decent job of kind of explaining where all this idea of polarity comes from, which leads into talking about intermolecular forces. It also summarizes a few of the intermolecular forces. This video is going to be more organic specific, and I'm also probably going to treat you guys like adults and show you some of the little bit more impressive items from this topic. So keep in mind, intermolecular forces, what we're talking about in the case of an intermolecular force is the strength of attractions between molecules. This is incredibly important and easy to confuse. We are not talking about the bonds within molecules. We are talking about kind of two ships passing in the night, those ships being particles of some bit of matter, and the kinds of interactions that they have kind of as they pass by one another. And it turns out that this influences, like you can probably read, the melting point, boiling point, and solubility. The two things in organic that we're going to concentrate for the most part on is boiling point and also the solubility, specifically the solubility in water versus other more organic things. So you should probably remember, and if you don't remember how to identify these, it would be a good idea to go back to that optional video. But I'm just going to assume you understand how to identify these various forces, and we're going to apply it to an organic context. So we have really in organic three different forces that we care about. Well, really four. One's kind of left off this list. One is the dipole-dipole force, which is something that will occur obviously when something has a dipole. In other words, when something has some arrangement of bonds in it that have enough of a separation of charge coming from differences in electronegativity that you actually end up with a slightly positive side and a slightly negative side. London dispersion forces, they occur in absolutely everything, but we usually only talk about them when we're talking about some sort of non-polar organic, like some sort of big giant hunky hydrocarbon, like for instance, gasoline or some sort of organic solvent or diesel or things like that. And we'll develop that idea a little bit more in just a second. And of course, you have lots of opportunity for hydrogen bonding once you introduce oxygens and nitrogens. And of course, these discussions are going to have everything to do with understanding the physical properties of different functional groups. And both amines and amides and alcohols and carboxylic acids and all those kinds of functional groups that if you look back at your functional group guide have OHs and NHs can certainly participate in hydrogen bonding. The one left off of this list, actually technically even two left off of this list, are the electrostatic attraction that's present in ionic compounds. It is actually possible, and we'll talk about several functional groups that make this possible, to make an ion from an organic structure. And those ions have intermolecular forces that we would term electrostatic interactions or ion-ion forces. But it's kind of specific to certain functional groups. So we'll kind of hold off on discussing that for a while. The other one that's left off of this list, that if you're really solid with your list, is the ion dipole force. And that's most commonly talked about in water solution. But usually if we're talking about organic chemistry, the solvents that we're going to be working with are not aqueous. Keep in mind the most important thing when assigning the types of intermolecular forces that are going to be happening in some sort of organic piece of matter, it turns out to have everything to do with polarity, that difference in between plus and minus charge. And most of the time in organic, it's a partial positive or a partial negative charge, which you'll often see designated with this dipole arrow. So we know that nitrogen, for instance, is very electronegative. Carbon is not. There's an electronegativity guide that's posted to, I think, the resource guides from week 1. And so we highlight that with what's called a dipole arrow, and it kind of shows us where the partially positive end is and then also the partially negative. So carbon in this case is going to be partially positive. I lost my arrow. Where is my arrow? Well, you can see it either way. The one thing that I wanted to build on a little bit is that it turns out that there's a whole bunch of different factors that play. It's not just the electronegativity, it's also their bond length and things like that. So organic chemists, or chemists in general, have come up with a quantitative system for measuring this thing. And the dipole moments are always going to be measured in debye, which is that capital D that you see there. So let's take a glance at a slide, and you can see some of the different dipoles. And you can also look at the way that we're going to kind of envision some of these dipoles with some pretty images in just a second. So here are just some really common organic things along with their molecular dipole moments, which are all measured in debye. So you can kind of get a sense for what the most polar things are and kind of the way that debye play a role. So you can see here that acetonitrile, which is a really polar solvent, it's got a big long dipole arrow, which is indicative of a really pretty decent sized dipole. And you can also see its structure right next to it. The interesting thing that organic chemists will do is quite often you'll see these electrostatic potential maps, and red indicates a site of partial negative charge or sometimes full negative charge. Obviously in this case it's just partial. But the way that you can look at this is you can find the most negative end and also the most positive end, right? The most positive end is kind of that blue color there. And as I mentioned in a previous video lecture, everything in organic really has to do with a nucleophile, something that is negatively charged or partially negative, approaching some sort of electrophile, which is partially positive charged. And so this idea of identifying the things that have a dipole is pretty important. As you might expect, the things that have greater dipoles have kind of a greater separation of charge and are kind of like a little bit bigger and meaner in terms of some of the properties we're going to talk about. So I'm talking about like the kind of the chemical properties of things in terms of reactions, but at this point in our learning, we're talking about physical properties. We're going to concentrate a whole bunch on boiling point. And one of the things that you'll notice is that the things that have really high debye numbers, in other words, a really high separation of charge, that acetonitrile is going to have a much higher boiling point because of the attraction between those positives and negatives relative to things with like a lower debye number. So let's just pick out this next slide here. So for instance, like chloroform, for instance, you can see that there is, a much lower debye number. And it turns out that for the most part, even though in general chemistry you would have labeled this thing as a polar molecule, and technically it is, you have a much lower boiling point for this guy because the separation of that positive and minus charge is so much smaller. You could see something like carbon tetrachloride, which is certainly overall nonpolar. Nobody would argue with that, which has a very, very low boiling point. The problem is that as we start kind of developing this idea of boiling point, is it actually turns out that the debye don't have the only thing to do with the boiling point. Turns out we also have like a certain contribution from the overall mass of an individual molecule. So you kind of have those two things that are competing factors, right? Sometimes competing, sometimes not, but you have the role of kind of the electrons separation, but also you have this role of, the weight of the compound and the electron density, and we'll talk about some specific kinds of forces now. The most important force for us in organic, because we're talking about these big giant chains of carbons and hydrogens that are not very polar, right? The difference in pole between carbons and hydrogens is not great enough to make them be a polar molecule. So we're, at least in terms of just the hydrocarbon backbones, we're almost always talking about a nonpolar thing. So that means that London dispersion forces, which is actually the hardest to understand, is going to be the most important one for us to talk about. So a couple of things just to list off is that this is one of the van der Waals forces, and it really is a temporary dipole moment. So, in other words, even if you don't come to the game with a dipole moment, just kind of the random distribution of electron density kind of temporarily being higher on one part of a molecule relative to another one can then induce the opposing charge in its kind of neighbor. And so this picture is decent, but I'm going to try to look for a really good animation of this thing actually occurring, because it really is transient, right? These two things will kind of just be this like random assembly of electrons buzzing around, and then just at any particular moment, you might have a little bit more of a buzzing electron cloud right here relative to right here. And when these two things start to come together, what happens is you get this kind of very temporary induced dipole, right? So the negatives attract positives there, which makes this side a little bit more negative, and then it induces another charge over here, yada, yada, yada. So the point is that if you're only talking about London dispersions, these can be very weak. But if you get a big enough cloud of electrons, in other words, some like huge molecular weight thing like diesel, right? Like, so let's compare gasoline to diesel. In fact, if we were in class, I would, burn some gasoline and burn some diesel. And what you'd notice is that with the gasoline, it's so much smaller, even though there's only London dispersion forces. Relative to diesel, which also only has London dispersion forces, the diesel burns much worse because there's so much less vapor there, because the diesel's molecules are held together by these fairly strong London dispersion forces. Right? In that case, diesel is a huge molecule relative to gasoline. And so even though I'm talking about dispersions as very weak, if you get a high enough molecular weight, it turns out that you can actually end up with some very high boiling points. Think of asphalt, for instance, right? That's just a hydrocarbon, but I don't know if you've ever worked on a roof, but it is nasty because that thing is just so hard to, it's so sticky it's really hard to get it off your shoes, for instance. And that is a very, very strong London dispersion force. So I noticed my old animation link wasn't working, so I found this pretty good representation of what's going on with induced dipole or London dispersion forces as an animation, and also the person narrating this video summarizes it pretty well. You'll notice that this is in terms of various elemental attractions. It turns out all of the stuff that he's talking about builds perfectly into our organic discussion. It's just that instead of talking about the differences in size between, say, a helium and an iodine, what we're going to see is we're going to be talking about low molecular weight hydrocarbons versus high molecular weight hydrocarbons. And he even goes into a little bit of that towards the end in terms of the effect of branching on the boiling point and the amount of London dispersion force in something.
Two helium atoms, the little flashy green lights, are indeed electrons and neutrons and protons in the nucleus. And if I slow time down and then stop it, you can see on the left-hand atom, the electrons and protons are on different sides, giving a temporary dipole to the atom. And those electrons repel the electrons in the adjacent helium atom and can lead to the formation of an induced dipole. And where you have negative next to positive, you will get an attraction, and that is the London dispersion force. It only lasts an instant, because the electrons are soon on their way again, and the attractive bond is broken. Looking down, group 17, the halogens, literally giving birth to salt. Ooh, I bet that would sting. Notice the trend in boiling points there. Fluorine's a gas, but at the other end of the group is iodine, the solid. Why is that? Well, it's to do with London dispersion forces. The more electrons there are, the more London dispersion forces there are. And so iodine has more electrons than fluorine, and that has more London dispersion forces and a higher melting and boiling point. You need more energy to break those bonds, a higher temperature. So, London dispersion forces. Well, let's start with these Morningstar Farm sausages. Wow, that's about as disappointing as you can imagine. And then we've got veggie meatballs as well. Okay, they look a little bit better. So I'm going to pretend that these are pentane, and this is 2,2-dimethyl propane. So come over here and video the cooking.
Please.
Please. So you can see that the sausages and the meatballs have the same volume, but they do have different surface areas. This has a smaller surface area, it's a sphere, and this has a larger surface area. So the sausages, there are more points of contact between them, which means they're going to stick together more than the spheres that are only going to touch at very small points of contact. And the reason for that is that sausages have a larger surface area, meatballs have a smaller surface area. And it's the same with London dispersion forces. The pentane has a larger surface area, and the 2,2-dimethyl propane has a smaller surface area. So this is having a higher boiling point, and these are having a lower boiling point. Start the video. You know, actually, it tastes like 2,3-dimethyl propane. So looking at this animation, you can see two molecules. Both of them had the same volume, but they do have different surface areas. The spheres on the right only make very, very small contact with each other, which means that London dispersion forces are going to be much reduced compared to the sausage shapes on the left, where there's much more contact when they collide each other. And rather labouring the point, here is the boiling point of pentane. You can see that it is indeed elevated above the boiling point of 2,2-dimethyl propane. So in summary, London dispersion forces are the weakest intermolecular force. They're due to instantaneous induced dipoles. They're temporary, and they increase with increasing number of electrons, and they increase with increased surface area. The way I remember this is sticky sausage, non-sticky balls.
I had to end with that, the non-sticky balls and the sticky sausages. Man, Brits have a disturbing sense of humor. But what he was talking about were specifically having to do with just simple hydrocarbons. And so we are purposely picking out isomers of each other, and we'll talk more about this on Friday, what exactly an isomer is. But you can see that the parts that you use to build them are the same, but you kind of arrange them differently. And that's important because all of these have the same number of electrons, right? And so all things being equal, they'd have the same opportunity for London dispersion forces. But what you can see is that shape has a big effect on the London dispersion forces. Even though each one of these has a London dispersion force going on, you'll notice that this really, really long chain has a much higher boiling point than something that you kind of arrange in a clumpy little ball, right? And so this is kind of one theme that we'll see in terms of boiling point over and over and over again. The more branched you are, the lower your boiling point is, and it has everything to do with surface area, just like what he was saying. So that basically just summarizes what I just said. So that's what we have to consider when we look at the same molecular weight in terms of all of these things have London dispersion forces. But what happens if we add more carbons to this hydrocarbon? What if we make the molecular weight higher? And that's where one of the resource guides will help us out. Here we can see what happens in the boiling point as you go from just one carbon all the way to 8 carbons. And by the way, these are all linear, so there's no difference in terms of their, the arrangement of their atoms. You can see that there's a pretty big jump in boiling point, right? And so the way I think about this is that octane has a lot more glue kind of holding together those molecules than something like methane, right? And so boiling point is one of the main ways that you measure intermolecular forces. It's a really common organic question to say like, hey, which one of these is going to have a higher boiling point? And one of the first things you do is you identify the types of intermolecular force that are happening. And outside of having any functional groups in there, if we're just talking about a hydrocarbon, quite often what we have to decide between is A, what is the overall mass of this thing, right? How many carbons and hydrogens does it have? And B, how are those carbons and hydrogens arranged? So hopefully that makes some amount of sense. That same kind of pattern that we saw, if we compare two different molecular weight compounds with the same functional group, you'll notice that even though these have some much more powerful forces going on in terms of hydrogen bonding and such like that we'll talk about in just a second, it turns out that the length of the carbon chain even here plays a role, right? And so butanol is going to have a much higher boiling point than something like methanol. And it has everything to do with recognizing, okay, well, these things both have hydrogen bonding, right? That's like the most powerful type of intermolecular force. But this like carbon chain length having to do with that London dispersion force argument still plays a role, right? And so we still are going to consider something with this long carbon chain to have a higher boiling point than something like this. And so if you look over here at octanol, obviously octanol has a much higher boiling point. So as I mentioned at the intro to this video, we're going to talk about boiling point, which we just did for specifically London dispersion forces. It turns out that solubility in water, specifically in organic class, also happens to be pretty important. So again, this is pretty well summarized in the optional lecture that I gave you guys. But just to build on it a little bit, keep in mind that like dissolves like. Polar solutes dissolve in polar solutes, and nonpolar solutes dissolve in nonpolar solvents. So really what this is saying is that if you have similar intermolecular forces, you will be able to mix freely. So what does this have to do with organic? Well, let's click on this slide here. And what you see here is some big giant long hydrocarbon, right, which only has London dispersion forces. It turns out that you have to have something with a whole bunch of London dispersion forces and nothing else, right, in order for this thing to dissolve. If you try to dissolve some sort of big giant long carbon chain thing into something which is polar, like water, right? That's why oil and water don't mix, right? In this particular case, this nonpolar solid just kind of hangs out as a booger on the bottom of your test tube, right? And so keep in mind, just about everything we're talking about has to do with a bunch of carbon. So it kind of inherently often is going to be insoluble if we're just talking about hydrocarbons. So there's different ways that we could build in functional groups to make it want to dissolve in this water, right? And so a really typical thing that I would do when I was in grad school is I'd figure out ways to make like certain drug candidates a little more soluble in the watery bodies of patients. And so you'd take some sort of drug that was kind of oily and you'd start putting on, let's say, alcohol groups or amine groups or things like that. And you'd hope that it didn't change its activity at all. And kind of in an attempt to get this thing to go into solution. This resource guide, you can see a little bit of that in the overall solubility of these things in water, right? Something with not many London dispersion forces is going to tend to be very soluble in water, right? And then given the same functional group, like between butanol and octanol here, you notice that as we add carbons to the chain, it becomes less and less soluble until you get to octanol, and this thing is totally insoluble, right? And so this is where that like dissolves like discussion comes in. So you might imagine if you needed something like this to actually dissolve, you might put another alcohol group in there, you might put something that's a little more polar on here, and in fact, things like soluble vitamin, like water soluble vitamins, like say vitamin C or something like that, has all kinds of different really charged functional groups or really partially charged functional groups that allows it to be soluble in water. Okay, so now we're going to build from just plain old hydrocarbons. Granted, those last couple of slides had a couple of different functional groups, but they were almost always the same functional group in a similar molecule, just of different carbon length. Now we're going to talk about specifically what's going on in some of those functional groups that have what's called a dipole. So keep in mind, this is only going to occur in if you're talking about a polar molecule, right? Dipole-dipole interactions. This is going to be a lot more polyab dual opposites attract, right? Whereas before we were talking about these temporary, really weak forces, dipole-dipole forces are starting to get a lot stronger because you actually have a positive and a negative end. So things with dipole-dipole forces are going to tend to have much higher boiling points. They're going to tend to be a little bit more soluble in water. And I think there's a part of your resource guide that highlights this pretty well. Unfortunately, it wasn't included in your resource guide on a second look here, but I did find a crappy looking table that kind of demonstrates what I'm talking about here. So, what we have here are a bunch of different simple organics, and they tried to compare their masses, right? They tried to pick out pretty much the same mass so that we don't have to consider the role of that. But what changes is the various functional groups that are present in each. And because of those different functional groups, you can see that as we go down the list here, our dipole moment increases until you get to good old acetonitrile down there. So even though these, are pretty much the same molar mass, you can see the huge role played by the strength of the dipole-dipole interaction. So you got things like propane, which are, they have no dipole, they're completely nonpolar, pretty low boiling point, 231 Kelvin. And then you kind of go down this list, and what you'll notice is you get a bigger and bigger dipole until finally, you've got like 120 something degrees or 120 Kelvin, greater boiling point, right? And so you can see that as the polarity of something increases, the boiling point definitely does as well. Hopefully at this point, this is just beating the dead horse, but this is what you can kind of think of when you think of dipole-dipole interaction, right? It's something like this, which has a dipole that kind of is a it's something like this that has a dipole, right? Where it's got an actual slightly negative end interacts with the slightly positive end of a neighbor here. And so this is a much stronger kind of interaction. And of course, as this arrow increases, right, if we get more and more Debye's in here, then you get a much, much higher boiling point, a lot more intermolecular forces. So as you might remember from Gen Chem, a special kind of dipole-dipole force is extra strong. So this is called hydrogen bonding. In terms of an organic context, you have to have some sort of NH or OH in order for this thing to happen within the same sample, right? You can have hydrogen bonding occur if you like mix two things together and maybe one thing has a nitrogen and another one has the NH or the OH. At least at this point, we're talking about just pure samples of these organics. So I call this the NOF-H-NOF, right? Because it requires some sort of nitrogen, oxygen, or fluorine that through space hits a hydrogen, which is itself attached to a nitrogen, oxygen, or fluorine. So that's called a NOF-H-NOF in my head. So here are some example of those hydrogen bonds, and you'll notice that this is the type of thing that occurs in alcohols and also in another group that we should know about called amines. This item in the resource guide is a really good look at the incredible increase in boiling point and because of the increase in intermolecular force when hydrogen bonding is allowed to occur. Notice that both of these things are isomers of one another, right? And this was dipole-dipole, which we said, oh, that's pretty strong, right? 35 degrees Celsius. Whoa, once you allow hydrogen bonding to occur, look at how much that boiling point goes up, right? A watch pot never boils for that reason. And you can see that this is the ionic form of an alcohol called an alkoxide. But when you make it ionic, which is a force we're not really going to talk about too much, you can tell that like having that kind of electrostatic attraction makes it a really, really high boiling point. I really like this that's included in the resource guide as well. This kind of shows you some of the various functional groups and the kind of attractions that they have, the intermolecular forces they have. So this might kind of help you to start off identifying like a functional group and then being able to identify some of the intermolecular forces. It also kind of ranks the strength of all of them. So make sure you check that out as well. So as you likely noticed previously, is when we talk about intermolecular forces, we can talk about the effect on boiling point, but another common thing that we'll have to talk about is its solubility in water. I like this one because it highlights some of the functional groups, and all things being equal, are they going to be soluble in water or not? The only thing I wanted to point out here, notice that carboxylic acids being one of the most polar type of organic groups, tend to be much more soluble in water than any of the other groups So you can see, for instance, like ketones. Yes, they have dipole forces, but it's not as soluble as, let's say, something like a carboxylic acid, which has hydrogen bonding. Right, hydrogen bonding tends to increase its ability to dissolve in water. So before we end, I wanted to point out some options for you in terms of like increasing your learning. Keep in mind, I always post various supplemental lecture slides that I sometimes use, like I did today, usually in a very different order than they're presented, just because it's convenient for me. But within those, there's a lot of different problems that have answers to them. Like, for instance, this problem is a really typical kind of question in organic chemistry having to do with identifying intermolecular forces, their role in boiling points, and solubilities, and all that stuff. So make sure you look at those if you're a little bit confused. And other than that, talk to me in those office hours. Take care.